Okay, let's start. This should be perfect. Hello everybody, this is Avantik here. Today we'll discuss pre-processing of data using scikit-learn. Let's connect it to the pipeline. Okay, first was business understanding, figuring out what you're trying to solve using machine learning and what is and how to get the data. Okay, that's what business understanding. Once you get the data, you need to clean it, you need to do some processing on it so that your visualization libraries like Matplotlib, Seaborn can actually show some interesting stuff out of it. Okay, so that is your visualization and getting the data ready for visualization or some maximizing the understanding of it is known as data wrangling. Okay, once you have done these 3 steps, you want to do some predictive analysis on the data. You want to apply some machine learning algorithms on it. But remember one point: you cannot apply machine learning algorithms directly on say text data. It does not understand text. You cannot apply it on images. It does not understand images. Okay, all it understands is numbers. So you basically have to convert whatever data you have received into vectors of numbers. Okay, that's what machine learning algorithms understand. Okay, so in this module of ours, we'll be discussing different techniques of vectorizing the data. Okay, also there are certain assumptions that the algorithms or the machine learning learning libraries have when they use the data for training itself. Okay, for example, if you talk about some of the predictive algorithms, it needs data to be normalized before it is fed to it, so that it can show better results. Okay, so we need to do data pre-processing so that we can convert the data to a format that algorithm is best suited for. Okay, let's start one by one. These are the things that we'll discuss: standard scaling, MinMax Scalars, RobustScaler, okay, normalization, binarization, encoding, categorical, that is ordinal and nominal features, imputation, polynomial features, custom transformers, text processing, CountVectorizer, TfIdf, HashingVectorizer, and using skimage. Okay, these are the things that we'll be covering in this module. Let's go to them one by one. Okay. The first one of them is standard scalars. Okay, let's first understand what is normally distributed data. Okay, so you must have seen earlier a data which has a Bell representation, or it is also known as Gaussian representation, right? So this is known as normally distributed data. Okay, this is the frequency or probability. This is the value. Okay, so any continuous value value can have this distribution where this is the middle chunk of the data which shows the heap, and there are some data which comes to this range, and this is the normally distributed data. So that is the prerequisite for this scaling technique to be applied. Okay, so all these scaling techniques, these are known as transformers, or all the data pre-processing techniques, these are known as transformers. Okay, transformers converts your data from one format to another format. Okay, so of course you can connect multiple transformers together. Okay, and the learning algorithms is known as estimators. So before you can feed your data to the estimator, you will pass it through multiple transformers. Okay, standard scaler is one such transformer. Okay, MinMax Scaler, your polynomial features, all these are transformers here. Okay. So coming back to standard scaler, what is one prerequisite that it needs? It expects, before it can, the transformer works, it expects data to be normally distributed. Okay, of this sort of distribution. This is the value, this is the continuous value, this is the probability of it. Okay, you can see the middle value have peak over here. Okay, so let's see further. Okay, so what you want to do, there are some algorithms which expects data to be standard scaled, okay, before they are fed to it. What does it actually mean? Say you have columns X, Y, and Z. Okay, so X is in kilogram, this is in gram, this is in milligram. Okay, so of course if kilogram 1 to 7, right, this is the value. gram may be few hundred grams, 1200, okay, but milligram it can be in the different scale itself completely, 1000, you know, to 2100, 3500, like different scale itself. So these three of course corresponds to weight, and these three are in different scale. So what a standard scaler does is it tries to bring all of them to same scale. Okay, so let's see how we do that. We have this data here. Okay, we are generating some data. This is first column X. This is the distribution of it. The mean of the data is 0. The standard distribution is 2, and we in total have 10,000 data. Followed by that, we have this another data which is mean of 5, standard distribution of standard deviation of 3, and the total data of this. So we have these 3 columns here, and if you try to plot all the 3 columns, right, this is how the plot shows up now. Okay, this is one column, this is one column, and this is one column. Okay, of course, if you compare to our situation of kilogram, gram, and milligram will be picked up high, right? Because the values will be in higher values, in thousands. Of course, the kilogram will be on lesser peak, right? So this is what is the initial data, right? When you apply many of the learning algorithms, it will find you how important is a particular column. So if the data is in different scale, the value that the algorithm predicts might not make a lot of sense for you, right? Okay, if it is not clear at this point of time, don't worry, because all these things will make sense very soon when we discuss about linear regression or other techniques. Okay, but and once you do that, feel free to come back and build this again. Okay, but before we do that, it's really important to understand PreProcessing. Okay, so you can see here data belongs to different scale. Now what will you do? You need to bring all of them to same scale. That is what standard scaling does. And how it does is it actually calculates mean of each column. Okay, for each column it will calculate mean, and it will subtract each value, mean from each value of that column, and divide it by standard deviation. Okay, and what will this do? This will bring all the data to same scale. You can see here the same data which was earlier, we applied the standard scaler. Okay, I'll discuss what is fit transform. We applied standard scaler, and in the resultant of it, all the 3 data became in same scale. That means this is very similar, right? That means be it in kilogram, gram, milligram, all the data are of similar values. Okay. Okay. So what is the nutshell standard scaling is doing here? It tries to bring data of different scale to same scale. Okay. Now let's get back to transformers. All these transformers, which basically transforms your data from one format to another format, supports 3 important APIs. One is fit. Okay, this is to create a mapping. Okay, say for example you are doing okay, in this case it might not do a lot, but it is creating a mapping for you. This string maps to this number. Okay, this is a mapping. So then followed by that you have transform. Okay, transform will actually take a data, and based on the previous mapping it will convert the data. And third one is fit transform, right? So fit will understand the relation between the data, and using the data it will later on transform the data, and fit transform will do both of them together. So all these APIs support these 3 functions: fit, transform, and fit transform. Okay, just to reiterate, your standard scaling expects data to be normally distributed. If your data is not normally distributed, standard scaling might not be a good option. We'll see next MinMaxScaler, which is a good option in that case. The next one is MinMaxScaler. It is one of the most popular data scaling technique. Okay, remember so far your standard scalers, your MinMaxScaler, and the next few of them will be working on numbers. Okay, on continuous numbers. Okay, so what the limitation of standard scaling technique was, it is not applicable, or it is not best suited if the data is not normally distributed. Okay, so let's get to a situation when data is not normally distributed, and let's see how this works out. So let's generate some data which is not normally distributed. As you can see here, we are generating three columns here. Okay, these are three columns: x1, x2, and x3. x1, x2, and x3. Okay, the x1 is positively skewed, x2 is negatively skewed, right? Okay, so you have data. This is normal distributed data. This is skewed distribution of data, isn't it? Okay, this can be either positively skewed or negatively skewed, right? So this is your distribution. So we have these three distribution of data. Okay. Now what we intend to do is, of course, the data is not normally distributed, so standard scaling technique won't apply. So what you do in the situation, you use MinMax Scalars. Okay. What does MinMax do to your data? It basically subtracts minimum data from each column. For each column, right, x1, x2, and x3, it will subtract the minimum value, and it will divide it by the difference between the maximum value and minimum value. What will this do to the data is the data will be now, in the range of 0 and 1. Okay, no matter what your data was in the beginning, now it came between 0 and 1. Okay, so that's what we are creating a MinMax Scaler instance, right? Similar to your standard scaling, we created a MinMax Scaler instance. We did a fit transform, so convert this data df to fit and transform together into data.df. And once we have done that, we want to visualize our data.df, and you can see here all the three data which was in differently skewed is in the same range here, right? Same range here, -1 to +1. Okay. So we understand now standard scaler and MinMax Scaler. Let's proceed to the next guy, RobustScaler. Let's understand RobustScaler. We have dealt so far with standard scaler, MinMax Scaler. Let's see why do we need RobustScaler at all. The first point is your data, of course, will not always be same. You will have some outliers. What is outliers? Data which does not fit the regular trend is known as outliers. Say, if you have this is one X column and Y column, if you do distribution of your regular data like this, and there is a couple of data which is really far. So you can say these are your outliers, right? Okay, so outliers has a serious impact when you're scaling the technique with MinMax Scaler or your standard scaler, right? Because you are dividing the data by the difference between min and max. Had there been some outliers, you will be dividing the data with the higher values, right? So there is an impact of outliers on the data. Okay, if you you're using MinMax Scaler or standard scaler. If you realize that your data has quite a few outliers, then you would prefer to use RobustScaler. Okay, what is RobustScaler doing is, okay, it actually subtracts, it divides, of course, the entire data into quantiles. Okay, 1, 2, 3, okay, 0, 1 to 3 quantiles. The objective is it actually subtracts the first quantile, not the minimum of the data, but the first quantile of the data. It means 25% of the data. So this is a data distribution. This is 0%. This is 100%. This is the min max. So what it does is 25% percentile of the data, right? Whatever value falls in this, it will subtract x1 by that. X1 means each column it will subtract the Q1 quantile 1 of the data, then divide it by quantile 3, that is your 75%. 75 this minus this, rather than max minus mean or mean in the standard scaling technique, it will subtract by this and this. So this is how, if there is some outlier, of course it will fall in the first 0 to 1 quadrant to 3 to 4 quadrant, right? Quantile that will be taken care of, right? That's how RobustScaler works. So in case you have outliers, this is the guy to go for. Okay, let's see how we generate. So okay, let's see here. We have two columns generated, and few of them has outliers. Okay, so there are few outliers over here. This is the normal. This is the mean is 20, standard deviation is 1, and there is 1000 data. Okay, this is the general trend, and this is the outlier. This mean is 1 and standard deviation 1, 25 points. That's why you see a lump over here. Okay, see a lump. Similarly, x2 is another column which has 50 as a mean of the data, 1 as standard deviation, and that's the lump here. So this is how the data is, right? Both the data. Now you really want to apply a robust scaling technique on this data to bring it in the same scale so that it works out and it is not impacted by the outliers. So you did a fit transform on using the same data. These are the columns, and this is what happens to the data now. Okay, so this guy works pretty well if there is some outliers in the data. Okay, let's get to the next scaling technique after this. Let's get to the next scaling technique, that is the normalizer. It's pretty interesting what it does. Okay, so let's see that. Let's generate some random data like this. We have three columns, x1, y1, and z1, right? And once we plot the data in 3 dimensions, this is how it looks like. Of course, this is the minimum, 100 is the minimum values, 100 is the maximum value, and you have 1000 data, right? This is how the data trend is, and you have 3 columns here: x1, y1, z1. These are your column names, right? Okay. Now what we want to do is we want to centralize the data. Okay, bring it closer to Excel. Okay, say we want all the data to be at unit distance from the origin. Okay, if you imagine, in a 3-dimensional axis, and you can see it here, each data will be a point, isn't it? This being x-axis, this being y1, this is z1, right? These are your features. Okay, so this will be somewhere here, right? All these points. What we want is all the data to be, at a unit distance from the origin. This is what is normalization. Few of the learning algorithm expect the data in this format. So you basically would need to normalize the data. Let's see how it is done. So how it is done is you basically divide your data for each value by square root of, say this is value A, B, C. So the new value of this A will be A square plus B square plus C square. This is what it would be. Okay, so what will happen because of this, all the data will be at unit distance from the origin. It would look something like this, right? All data is at a unit distance from the origin, isn't it? Interesting, isn't it? Okay, same, you will, all this, scaling techniques, pre-processing methods, everything is present inside scikit-learn pre-processing. So is this guy normalizer. You're creating an instance of it, you are doing a data transformation. Okay, and what it does is it brings all the data at a unit distance from the origin. Okay, let's see the next method, binarization. As the name implies, it will convert your data into zeros and ones. Why do you need it? There are few algorithms to be named. One of them is Bernoulli's naive-Bayes. We'll come across this when we'll discuss naive-Bayes. It expects your data in Bernoulli distribution. Okay, what it means, data should be in zeros or ones. Okay, so given a particular data like this, okay, it can consist of any value. It needs to be converted to a data like this of zeros and ones. Okay, so what we do, we use this binarizer, which is present in the pre-processing library, create an instance of it, and of course do a fit transform after that. The data is now in this format. Okay, remember some of the algorithm expects it. So you have a inbuilt pre-processing binarization technique over here. let's get to dealing with categorical values. Okay, let's understand what it is first. Not always your data will consist of numbers. We have dealt with scaling techniques which will deal with continuous numbers and all, but not always that will be the situation. You'll get strings like a column with gender, male, female. You'll get, salary column as low, medium, high. You'll get location, right? And many such things, right? Okay. So let's see how to deal with categorical values. What are categorical values, first of all? Like, for example, you have income as low, medium, high, right? You have gender as male, female. You have location, you have fruit names, you have vegetable names, you have policy type, right? You have infinite of such options. These are your categorical values, one string word, right? A couple of words. So that's what it is, categorical values. Now, categorical values can be of two types: ordinal values and nominal values. Ordinal value means there can be a relationship between the values itself. For example, in this case, you see you have low, medium, high, right? So of course, low should be lesser than medium and medium should be lesser than high. So okay, and remember your machine learning algorithms do not understand strings. It has to be converted into numbers. Okay, so here we learn how to convert this categorical values into numbers. So this is how our data frame looks like: age and income. Okay, so what we can do is you can create a mapping dictionary like this: low 1, medium 2, and high 3, and we can do this transformation over here. It will return you a column which has converted low to 1, medium to 2, and high to 3. We'll see how to put this in code later on. Now comes to the encoding part of nominal values, right? Nominal value means like male, female. There is no such order there. Okay, so remember, if you don't have an order and you put there 0 and 1, you're actually inducing some order, right? Which was fine as long as there is one order in it. That was the case with ordinal values, but for nominal values, this is not fine. What you have to do here is you actually have to convert your data into one-hot vectors. Okay, what is one-hot vector? So one-hot vector means, say you have male, female. Okay, male, female. This is two options. So of course, if you make male 1, male 0, and female 1, or maybe 1 or 2, you're inducing some order, which is not true. So what is the correct thing to do here is you create two columns. One is male column, one is female column. Whenever the row is talking about male, you mark this as 1, this as 0, and otherwise like this, right? So this is what is known as one-hot encoding. That means the entire vector will be only one entity will be present, be it male, female, only 2 values are there. Be it location, there can be 10 value, only 1 is present, rest of them is off. So this is one-hot encoding technique. So for that, you have to use two transformers. One is label encoder, one is one-hot encoder. Label encoder converts a string to number. It does not really take care of the order, just whatever comes first, it will convert a string to number. So we'll use first label encoder, and after label encoder, it returns the gender column like this, 0. So made female 0, male 1, right? That's what it did. So it introduced a new column over here. But remember, this is what we don't want. We want in one-hot encoded format. So we will now pass this particular column to your one-hot encoder, and this is what it returns. First guy is male, right? So that is why this is 1, 0, 1. Second, first column is male, 0th column is female, right? So this is how the one-hot encoding works, right? So just to reiterate, for encoding categorical values, based on the type of it, you might want to use different techniques. We'll see after this imputation. Imputation is another pre-processing technique. Okay, in the stage of getting data ready for machine learning algorithms, we need to know that if there is missing values in the data, machine learning algorithms won't work. It will throw error, or some unexpected behavior. Okay, it won't work. So let's create a situation. So this is the data which has few NaN, right? This is how you're creating missing values over here, np.nan, right? This is a data frame which has these two values missing. So imputer is a preprocessor which can actually provide some mechanism of filling in this missing values, right? So from preprocessing or importing this imputer strategy is mean, okay, and access one, okay, access one along this direction, okay, this is axis 1, along this direction this is axis 0. So what it is doing, it will calculate the mean along axis 1 and it will fill in the missing values with that. Okay, since I have this value axis 1, okay, I have axis 1 over here. So say this guy, in this fourth column or fourth row, you have this guy missing and this value is 4, right? So of course 4 divided by 1, okay, that is 4 here, that is why you see 4. Okay, and this guy again 4 and this is missing here, so this guy is 4 here. If I change this to x is equal to 0, it will calculate mean along the column. Okay, and number of entities will be number of nominal values, that is 3 plus 4 plus 1 plus 4 plus 5. I think this boils down to 17 divided by 1, 2, 3, 4, 5, 5. So it should be something around 3.4. This is imputation. So you have techniques like standard scaling and MinMax Scaler for or RobustScaler for your continuous numbers. Then you have encoding techniques for categorical values. Then you have imputation for missing values. Polynomial features is the next pre-processing technique we'll be discussing about. Let's first understand when you use it, and later on when we use it, we can actually come back and revisit this. Okay, for many algorithms, right? Say we have this column x and y. This is your independent column, and say this is your target, right? So when we'll learn in the next chapters that what you're trying to do here is you're trying to find a relationship between the dependent columns and the independent columns. That is what is machine learning, right? In simple steps, you're trying to find the relation. So if your relation is something like this, 5x plus 2y, right? Just in a simplest step, right? So what you're trying to do, here 5 times of x plus 2 times of y is is helping you predicting the value of t. Sometimes this linear relation is not sufficient. You need a polynomial degree relation, say something like 5x square plus 7xy plus 2y square. Now this, so sometimes your t is this, which is a simple linear relationship between x and y. Sometimes you need a higher degree relationship. Okay, so you need a transformer, and what you need to predict in using machine learning is this guy, right? So you need a transformer which actually convert your basic data to x and y into a higher degree data, so that your algorithm can derive coefficients out of it, right? So even if these things are not clear as of now, don't worry about it. You will please come back to this topic after you have done some of your machine learning algorithm, okay, in the latest part of the series. Okay, then it will make much more sense, but know it for now. Okay, so what you have, this is your data frame now, A and B. You have, this is the column, this is the column, the data frame now. And what you're doing here, we are creating a transformer, polynomial features. Okay, what is this transformer doing here? Okay, and so let's just delete this part, just before it. So let's now create it in the code and see how it works. So what you're doing here, you're creating an instance of polynomial features and passing a degree 2. So that means you're interested in degree 2 till degree 2. So what is like converting these two columns into degree 2? You'll have x square, y square, xy, okay, and of course you will have along with this you have x, you have y, and a constant factor, right? That's what it is. So given the data, we have 2 and 3 here. This is x, this is x raised to the power 0, right? This is x raised to the power 1, this is y raised to the power 1, this is x square, this is y square, this is xy, right? This is what it is doing. It is transforming your data, which was like this, to like this. That is your polynomial transform or polynomial feature. Let's see the next guy, which is our custom transformer. Custom transformer. So not always whatever you need, what sort of transformation you need for your data is available in inbuilt scikit-learn. Okay, you might have to define or create your own transformer. Okay, and of course it will be reusable. So let's see how to do that. So we are creating our own transformer, be it whatever we need. Okay, so for that we need to import this function transformer. In function transformer, we have to pass two things. One is the mapping function over here, okay, which will basically take a column and do the transformation for it. Okay, this is another column and it will do the transformation, right? This is the mapping function. So our data frame has two columns, age and counter. This mapping function adds 2 to the age and multiplies to the counter, right? And validate is equal to false. You have to do, remember this, you have to do to take care of strings. Okay, have a string column here and see the error. So for that you have to do validate is equal to false. Okay, so once your transformer is created, the mapping function is ready and everything around it, you need to pass the data frame here, and you can see the change, the transform data frame you're getting. So you can design your own Python functions or do whatever you can, and okay, you can decide your own Python functions and all, and this transformer will actually transform your data from one format to another, right? I'll do this custom transformer for one more time. Next one is your custom transformer. Not always whatever transformation you need will be available in scikit-learn or any such library. You might have to design your own custom transformer. Okay, so for that you have to import function transformers from your preprocessing library. So it consumes the mapping function. This is your mapping function. This is the transformation that you want to do. Say you want to add 2 to the age column and multiply 2 to the counter column, right? This is what you're doing over here, and you are doing this validate is equal to false. What is happening when you do validate is equal to false? Without this, it won't let you to deal with strings. Okay, so as an experiment, try to create a data frame with string column here and do not pass validate. You'll see the error, and once you put validate is equal to false, it will take care of that. Okay, so this is a transformer that you have created. Like earlier, it has this fit transform. So what we'll do here, we directly do transform over here because there's nothing to learn over here. This is the transformer. You're calling the transform function, passing the data frame. You can see here this each column is added to and the counter column is multiplied by 2. Okay, let's go to the next transformer. Text, and text is something you'll deal a lot with. Okay, but your machine learning algorithms do not understand text. It needs to be vectorized. That means it needs to be converted into numbers, right? So there are some transformers which enables you to do so. One of them is CountVectorizer. Okay, so let's take the data first and try to understand how to deal with it. Say you have a data frame which looks like this. Okay, of course there can be other columns, but there is one column text, and it consists of this text. Of course, now no length is not fixed and all, right? It can be of any length. This is the text. Now, how do you vectorize this data so that you can feed this to machine learning algorithms? Okay. So in sklearn feature extraction text, you have the, it is not inside processing, right? It is inside feature extraction of text. You have CountVectorizer. So how does CountVectorizer do? Count, how does CountVectorizer do this vectorization? It actually finds the frequency of each word, right? So it creates a vocabulary which is like unique words in the text, okay, and it assigns one column for each word, right? So maybe this is one column, this is one column, first is one column, and for each row of data it will mark, it will like first guy has one time this, and one time is one time first, right? It will keep marking wherever the words are present, right? So, and if like in this guy, second is appearing twice, so the column corresponding to second will have a value 2. Okay, if the value is not present, it will mark as 1. So, and of course, you lose the sequence in this process, right? The sequencing is the words appeared in the text is no more retained, it's lost. Okay, so there is no context as such. Okay, so once you create a CountVectorizer, you're passing data to this. But remember, this CountVectorizer, TfIdf, and all other this technique returns a sparse array. If you don't do this to array, it won't show you the output. Okay, it will show that sparse array. So if you want to see the contents of it, you have to do to array. But remember, if you're trying to do to array of a huge array, your Jupyter notebook or the application might be hopped. So be careful. Okay, this is the column vocabulary I was talking about. And is zeroth column, not one. This in this case, and is 0, awesome is 1. So you can see it tries to maintain the dictionary, the increasing order. And you can see here this is the column number. So if in the first guy, in the second column, this second word was appearing twice, right? This guy, second word is appearing twice. That's why the counter is 2 over here. CountVectorizer and the TfIdf vectorizer and the following one, HashingVectorizer, takes a couple of important hyperparameters. We haven't dealt a lot with hyperparameters so far, but any such transformer or estimator takes this configurable parameter by which you will be configuring this transformers or estimators. This is known as hyperparameter. So CountVectorizer in this case, vocabulary is a hyperparameter over here. So when you mention vocabulary is equal to mission, food, and second, all other words do not matter anymore. So one column will be for mission, one column will be for food, one column will be for second, and none of the other words is getting considered. So you can see this the second row itself again, only second column is present, nobody else, nothing else, right? So it is 0. So this is useful. So this vocabulary thing is useful when you're talking about vectorizing a text, which is a review comment for a bus service versus a review comment for a food service, right? Because words like tasty, fresh are important when you're talking about food, right? Food review. Okay, if somebody writes a review, the food is awesome, awesomely fresh. So you have the word awesome and fresh. So this is more suitable in terms of food industry, right? You will keep that in your vocabulary because you cannot have infinite words, right? In the number of columns, what are the number of words in English dictionary? The base words is around 3 lakhs. So you cannot have 3 lakhs and do the processing and machine learning on top of it. So this is the way to minimize the column size. The other vocabulary, other hyperparameter is stop words, D and E. So these are the words you don't want to consider. So the final result will not have these things in it, right? D and E. Also, there is another hyperparameter, n-gram. N-gram means number of words that you are considering. So in n-gram, you can pass 1 or 2. So let me show an example of n-gram. You can, okay, let's see this n-gram. So what we have here is, this is what it looks like. So you can see earlier there were only 9 words or so. Now after we increase the n-grams, this is what has happened. But what does it actually mean? If you do vocabulary, okay, it will actually show you, okay, single words are there, double words are also there. That's because n-gram ranges from 1 to 2, right? So you can see double words. That's why it increased, because sometimes words like not good is present, which is a negative feeling, negative sentiment, right? So this is how it helps here, because if you take not and good separately, then it's not the same meaning. So you need not good to be present, right? So this is what is n-gram. So remember these 3 hyperparameters: stop words, vocabulary, and n-gram. The same hyperparameters is applicable to TfIdf vectorizer, which is our next transformer. TfIdf vectorizer. CountVectorizer gave you the frequency of the word. Okay, it really didn't give you how much important that word is. Okay, this is the story. This is the riddle TfIdf vectorizer is trying to solve here. So as we see here, okay, on applying TfIdf vectorizer, it is returning value in the range of 0 and 1. So where words or the numbers, words corresponding to which the value is closer to 1, that means those are important words. Now the question is, how does TfIdf vectorizer figure out which one are the important words or which one are not important words? So so I'll use this term here, corpus. Corpus means collection of documents. Okay, so you have a document and collection of document. So let's say you have a Wikipedia corpus where each of the document is talking about some celebrity. So if you find a document, if you find words like parliamentarian, politician, and of course this will be important. These words will be important compared to the entire corpus, because the chances of this word being present in entire corpus is less compared to this document. So this is term frequency and inverse document frequency. How much important this word is to this document versus the entire corpus, right? Words like is, the, it will be appearing in this document as well as the entire corpus. That's what dilutes the importance of it. So you can see here the second word that is present, right? The second word, this guy second. So what happens is, this guy, since it is appearing 2 times and it's not nowhere else to be appeared, so this becomes a very important stuff. And that is where when you do TfIdf vectorizer, you can find out the second. This is the second column. If you do get feature names, it will give you the columns, and second is this guy. So you can see it's pretty much close to 1. That means it is becoming very important. TfIdf vectorizer, again a technique to vectorize a string. So you can have CountVectorizer or TfIdf vectorizer. Let's see the next transformer, which is your HashingVectorizer. Now, whatever technique we have seen earlier from dealing with text, like your CountVectorizer or TfIdf vectorizer, the size of the vector increases with the size of the vocabulary, right? And the amount of vocabulary for English dictionary is quite large. I think 3 lakh words are there in English dictionary, and of course you have slangs, you have derived words, so it becomes very difficult to deal with techniques like those, right? So you need a more powerful, robust technique. So that is where HashingVectorizer comes into picture. Okay, the first important point to understand is you can basically control what is your encoded vector length. Okay, so that's how you do it. HashingVectorizer, you're importing from feature extraction.txt, and you're mentioning the length of the width of the vector, so 5. No matter what is your vocab size, your final vector size is just 5. Okay, so the same text earlier, and you can see it's converting data in this format. So it will be in negative. Remember this. If there is some algorithm which does not accept this negative, you might have to do some more hyperparameter tuning over here. But okay, just check it out. And this HashingVectorizer is capable of doing out of code learning, right? The other 2 techniques, everything has to be in memory. Okay, only then those guys will work. So this guy, you can actually take some data, pass to it, you'll get some output, right? Okay, so you can do out of code learning. That is, if the data is too large, This is the technique that will work, not the other two guys. Okay, just remember this at this point of time. Later on, we'll try to use. Okay, that comes your hashing vectorizer. So far, we have dealt with continuous values using scaling techniques, categorical values, uh, then came out strings, right, text, right. So now time to deal with images. We'll use skimage for this. Skimage is not installed by default in your system. So you might have to do pip install skimage to make the installation go through. Remember, let's first load a data and see how does the image look like. So skimage.io, im read and im show. This is to read the image from a file, right? This is the file. I'm trying to read the image, and I'm trying to see the shape over here. So when you see the shape, this is the width of it, this is the height of it, and this is the depth of the image. Depth means RGB, right? And see the values of the image. The values of the image will be in the 0 to 255. That's the pixel value, right? Okay. Okay. And if you want to show the image, im show and the numpy array. So what is the important thing to understand that the im read function actually has converted the image into numpy, and you can use im show to show that image over here. You can convert the image into grayscale. Grayscale means, this is what RGB to gray. It's converting the image to grayscale. Grayscale means there will not be RGB assets. There will be only one dimension. That's what happens to the data, right? You do this. If you want the image to be resized, right? If you want image to be resized, okay, you can use the resize API, skimage transform. The skimage is again a very powerful library. It has a lot of options. You can use resize to convert the image into 200 cross 200, right? And this is what you are seeing over here. The image is now into 200 cross 200, right? Okay, that's all from the transformation part. Okay, where here we learned about the pre-processing, options that skimage, the pre-processing options that scikit-learn provides you. See you guys in the next video. Thank you.